Hey guys, let's go ahead and do chapter 2. This is on chemistry, and I know that tends to not be everybody's favorite subject, but the chemistry for this course just goes over what you need to know to be able to understand some basic biological processes as we move forward. So it's not going to be super intense as far as like what you get if you're actually in a chemistry class, but there's a lot of vocabulary. So when it comes to studying for the quiz for this chapter, you're going to need to know vocabulary and what else am I going to give you? Let's do that. I don't think I'm going to give you anything too hard. Okay. All right. Having said that, let's get started. Okay. Some stuff around on my end as usual. All right, so again, this is chapter 2. It is basic chemistry or essential chemistry. And again, essential meaning it's essential for biology for this course. All right, so let's start with some definitions. I guess we'll put what chapter this is. Okay. All right, so let's start with matter. Matter is anything that occupies space and has mass. Okay. So pretty much everything that we can see in the world around us is matter. And even things that you can't see is still matter. I mean, for instance, you can't see the air in a balloon, but you can see that the air is in there and that it's taking up space because the balloon is inflated. Okay. So all of these things are matter. Then we have mass. So mass is the measure of the amount of material that's in an object. Okay, so mass and weight are not interchangeable. Those two terms you can't switch back and forth. Mass is the amount of material in the object. Weight is a reflection of gravity acting on that mass. Okay, so for instance, this is where they do the whole thing like if you went to Mars or if you went to Saturn, what would your weight be? Well, that's because your mass would stay the same, right? If you went between Earth and Mars and Saturn, if that were possible, your mass wouldn't change, right? But the way that gravity pulled on or acted on that mass, sorry, would change. Okay, so mass and weight are not interchangeable. Okay, another basic term here is element. An element is a substance broken down into other substances. Right. Okay. Sorry, guys. So elements are things like what you see on the periodic table. We're talking about carbon, nitrogen, hydrogen, oxygen, iron, sulfur, silver, gold, bronze, all of the copper, all of these things, okay? These are all elements and you can't make them smaller through a chemical reaction. They can, how do I put this? Actually, I'm getting ahead of myself, so I'm not going to put it yet. I'm just going to tell you. So elements, what you find on the periodic table, and you can't break them into something smaller, okay? All right, let's talk about trace elements. Trace elements are elements that we require for our health, but we only need them in small or trace amounts. Okay, So some examples of trace elements are things like fluorine or fluoride, iodine. There's a whole bunch that we need, but just in small amounts. And a lot of times we'll find those trace elements incorporated into our foods. So if you look at like the nutrient panel on cereal or on all kinds of stuff, anything that you eat, a lot of times it includes really tiny amounts of these trace elements so that we make sure that in our diet, we're getting those consistently, okay? All right, so when it comes to all of these elements, our body requires, or I'm sorry, our body is made up of 4 major elements, okay? By major, I just mean they're really important for life. And those are carbon, nitrogen, oxygen, and hydrogen, okay? You're gonna see these over and over and over again, not just for this chemistry part, but as we move forward into other parts of biology, you're going to encounter these 4 elements because they like to make bonds with each other and with other elements, okay? So they're really important for life because they can bond to all kinds of other elements. Okay, so let's talk about compounds. Compounds are substances that contain 2 or more different elements in a fixed ratio. Okay, so water is a compound, right? And it's a compound because we can break that down in a chemical reaction into its separate elements, which are oxygen and 2 hydrogens, okay? So water is not an element in the chemical term. It can be broken into smaller actual elements, okay? The fixed ratio part is important because, using water as an example, we can have H2O, right? That's water. Fantastic. But what about this? What is H2O2? It has hydrogen and oxygen in it, just like water, right? So is it water? No. This is hydrogen peroxide, which you don't want to drink, okay? So the fixed ratio part is important because in a compound, all compounds of water will contain 2 hydrogens and 1 oxygen in that ratio, 2 to 1. And all hydrogen peroxides, 2 hydrogen, 2 oxygen in that ratio. Okay, so that is important. Okay, doing okay with all the vocabulary? I know there's a lot of vocabulary, but hang in there because we're going to do more. Okay, I'm going to skip a little bit, or I'm going to skip a line, I should say. Okay, we talked about elements being something that you can't break down into smaller parts through a chemical reaction, right? So I can't take oxygen and break it down into some other chemical. It's just oxygen, okay? But now let's talk about atoms. Okay, so an atom is the smallest unit of matter that still has all of the characteristics of the element. All right, so I need you to switch your brain for a minute from thinking about things on the large scale that we're used to looking at every day. And I need you to go way down past even the cellular level into an atomic level, which is so tiny, right? Can't see them. We can't put them under a microscope. So if you can switch your brain from big, like we're used to small. It will kind of help you process the information when it comes to stuff on the atomic and subatomic level. All right, so we have atoms, right? And if you have one carbon atom, you have the element carbon, right? So you don't have to have 100 carbon atoms to have carbon. All you need is one atom of carbon, which is why it's the smallest unit of matter that still retains all the properties of an element, because a carbon atom is different from an oxygen atom. Okay, so they're both atoms, they're both going to have the same subatomic particles, but they have different numbers of subatomic particles. And this is really important because those numbers of the subatomic particles, which are electrons, protons, and neutrons, those numbers are what make each element unique. Okay, so let me go into this a little bit more. Be patient if you don't quite get what I'm trying to say yet, because I got more explaining to do. Let's start with going over what these subatomic particles are. The subatomic particles are little tinies that are within the atom. Okay, and we're going to start with protons. Protons have a positive, here we go, have a positive charge. Okay, positive charge, and they're found in the nucleus of an atom. Then we have something called neutrons. Neutrons have no charge. They're neutral. It's the neutron, they're neutral. But these are also found in the nucleus of an atom. Okay. And then finally, we have our electrons, which have a negative charge. Let's try that again. Here we go. And these are found in shells, sometimes called orbitals around the nucleus. Okay. So, no, that's not what I wanted to do. Let's try this. Okay. So if this is my nucleus of an atom, right, my nucleus is going to have protons in it and neutrons, right? And then out here, I've got this shell. And the shell is where, good grief, you guys are subjected to more of my drawing. Huh. It's dented. The shell is where the electrons are. Okay. So you've got the nucleus in the middle, and then the electrons that are in the shells around it. These are often called orbitals because, as you can see, when it's drawn like this or presented like this, it kind of looks like planets orbiting the sun. And if that's the easiest way for you to picture this, how this system works with subatomic particles, go for it. If you get into more advanced chemistry, you're going to find that's not really quite the correct representation, but this works at this level fine. Okay, so you have these electrons out here, and the protons and neutrons are kept away from other elements by these shells of electrons. Okay, the electrons are the ones that interact with each other. So for instance, with water, I have my hydrogen atom here with its electron, only has one. And I'm going to have an oxygen atom and it has more. And I'll show you how to do, or just how I'm drawing all of these. I will show you how to figure out how many electrons go where, for those of you that want to know. Okay. And so then if I have my other, so this is oxygen, and these guys are hydrogens. Can't draw an arrow. Okay, so what's happening is, notice that the nucleus here in the middle is untouched, right? There isn't any way for the nucleus or even the electrons of this oxygen atom to touch this hydrogen nucleus, right? Because those electrons are in these protective shells around it. But when what happens is the electrons, again, are going to interact with each other. So in order to have a molecule of water, you have the hydrogen electron sharing here with this oxygen. And then this hydrogen electron is going to share right here. It's the electrons that interact with each other. They're kind of like bodyguards for the nucleus, if you will. Not because they actually have a protective role, but again, if you can kind of picture that in a way that lets you see that it's the electrons that interact with each other, and not the electrons interacting with the nucleus of other atoms, by thinking about them as bodyguards. Whatever analogy you need to kind of help you understand what this all means. Okay, so how did I figure out how many electrons to put? I wasn't just making up numbers. We're going to look at, no, that's not what I wanted. Too late, it's what I got. Okay, we're going to look at periodic table. I hope. Sometimes when I share my screen, it doesn't work. So give me just a sec to pull this up. And this one. All right, I'm going to try to switch over now to the periodic table. Okay, so here's a periodic table of the elements, right? Now let's go ahead and take a closer look at it. My stuff around. I'm going to use an obnoxious paint color because it probably stands out. All right, so I just did water, or drew water for you, which is H2O, right? So here's my hydrogen, and here's my oxygen, okay? The way that I can figure out how these are going to interact is by looking at something called the atomic number. I'll type this stuff out for you in just a minute. I'm just going to explain it first. So the atomic number tells us the number of protons in the nucleus. Okay, number of protons in the nucleus. Do you remember when I said a couple minutes ago that a carbon atom is not the same as an oxygen atom? This is why. It's because the number of protons in the nucleus of each different atom is different. Okay, So that's what makes them distinct from each other. So hydrogen, for example, has an atomic number of 1. That's what that is up there in that corner. I know it's a little blurry, but oxygen has an atomic number of 8. Okay. And carbon, which is right here, has an atomic number of 6. That means that all of the different carbon atoms on the Earth all have 6 protons across the board. Okay, they all have 6. Even if it has like a carbon 13 or a carbon 14, if you already know what that is, if you don't, no worries, because you're going to, still has 6 protons. All oxygen atoms, the entire world, entire universe, 8 protons. Okay, and that's how you can tell them apart. All right, the next thing you need to know is on these, how to read an atomic or a periodic table. Is this right here, the atomic symbol. And again, like in hydrogen, the symbol is H. See H, it means hydrogen. Carbon is a C. Oxygen is an O. Okay, this one over here, this is calcium, has an atomic number of 20, and its chemical symbol is Ca. That's calcium. Okay, all right. Now you do one. I want you to try to find it on here. Yes, even though I'm not staring at you, I still want you to do it. Well, I mean, I am staring at you. I'm just not in person staring at you. I still want you to do it. So I want you to find sodium. And sodium is one of those elements whose initials don't match the English name. Sodium, the abbreviation is Na. That's its chemical symbol. So go ahead and look at the periodic table, find sodium for me, and then tell me its atomic number. Just sitting here waiting for you to look. Did you find it yet? Okay. Sodium, Na, is right here. What was its atomic number? 11. Okay, so all sodium atoms in the entire universe have 11 protons. Do one more. Find, which one should I have you find? Find zinc for me. Zinc has a chemical symbol, Zn. Find zinc for me. And tell me its atomic number. Okay, so zinc is right here. And it has an atomic number of 30, which means what? That all atoms of zinc in the entire universe have 30 protons. Okay. This last thing down here is called the atomic mass. And in these, it's very hard to read, but you can see that there's 2 numbers here. I'm actually going to look at carbons. Carbon says 12.01. That's the atomic mass of carbon. I'm actually probably not going to give you, I'm not going to quiz you on this, but I'm going to tell you what it is, because otherwise it leaves part of what's on the, the square for each element. You don't know what it is. So the atomic mass is basically saying if I took all of those elements, or I'm sorry, all of the atoms of that element, even the ones that are kind of different from each other because they're isotopes, again, we'll get into that. If I take all of those and somehow was able to weigh them all, this would be their average weight. Okay, for smaller elements on the periodic table, it tends to be pretty much double the atomic number, but you'll notice as we get down here, actually you can't notice it because it's hard to read, but as you get down here, you'll find that the atomic mass is much bigger than double the atomic. That was information if you want to know, because you're like, hey, why didn't you talk about this last thing? I'm not going to put that on the quiz because we don't really need to worry about it for us. Okay, go back to my whiteboard here. All right. Let me type these things out for you so that you kind of have those notes. Again, we've got the atomic number, and this is the protons and nucleus of an atom. Each element has its own specific atomic. Okay. Again, carbon is 6, oxygen is 8, hydrogen is 1. Okay. Own specific atomic number. All right. Then we have, here's a term I didn't give you because you can't see it on the square. It's not portrayed anywhere. But talk about mass number. Mass number is not the same thing as atomic mass. I know. Whoever came up with all the terms for chemistry was like, let's make the terms as confusing as we can, because let's make them all sound like each other. Atomic mass, you don't need to know. Mass number, you need to know. Okay? Because the mass number is the total of all the protons and neutrons in the nucleus of an atom. Okay? So here's the question. Well, how do I know how many protons and neutrons there are in the nucleus of an atom? I'm going to tell you. Glad you asked. The way that you know is using the atomic number. Okay. So let's do this again. Carbon. Carbon has an atomic number of 6. I'm going to write this out. Protons, neutrons, and electrons. We're going to add that in. So carbon has an atomic number of 6. How many protons does it have? 6. Okay. Now we're going to use this atomic number to fill in the rest. In a standard atom, carbon also has 6 neutrons. And guess what? It has 6 electrons. Impressive, right? This makes carbon in this form completely neutral because the charge from the protons and the charge from the electrons cancel each other out. Okay. So if I'm looking at the mass number, if I need to find it, this is what I do. I add the number of protons plus the number of neutrons to equal the mass number. Or in other words, for carbon, I'm going to add 6 plus 6 to get a mass number of 12. Let's do it with oxygen. Oxygen has, what was that I just did? Oxygen has an atomic number of 8. Protons, neutrons, electrons. So how many protons does oxygen have? 8, right? Because that's the atomic number. Okay, standard atom, I'm going to have the same number of neutrons as I have electrons. I have 8 across the board. Now, I need the mass number. How do I figure out the mass number for oxygen? Take the 8 protons plus the 8 neutrons, 16. Oxygen has a mass number of 16. Okay. Let's do sodium, which is our Na. Sodium has an atomic number of 11. Protons, neutrons, electrons, you know the drill. How many what's the, what am I trying to say? How many protons in sodium? 11. Neutrons? 11. Electrons? 11. Mass number? 11 plus 11 is 22. Okay, kind of get how that works. So that's the mass number. Now the mass number is important because we're going to use it when we deal with the non-standard atom. That's right. Again, why make it like completely uncomplicated and non-confusing? Let's add variations. So you have your standard atom, which is where protons, neutrons, and electrons all match up. And then you have other types of atoms or other forms of atoms called isotopes and ions, because let's make them both start with the letter I. All right. Yeah, let's start with typing. All right, so isotope. Isotopes are atoms with the same number of protons, different number of neutrons. Okay, I'm going to throw in some vocabulary here to make you feel fancy. Essentially, this means that they have the same atomic number as other atoms of the element, but they have a different mass number. Okay, in other words, oops. Having issues here. Okay. In other words, so the same atomic number, same number of protons, but a different mass number or different number of neutrons. Did you just say you wanted to do examples? I'm so glad, because we're going to do examples. All right, we're going to start with the normal or standard version of carbon, which is carbon 12. Okay. Protons, neutrons, and electrons. Okay. Now remember here, I'm going to put up here, carbon has an atomic number of 6. Okay. All right, carbon 12. This is a standard atom of carbon, which means we're going to have, what's our number of protons? It's atomic number 6. Standard atom, neutrons are 6, and so are the electrons. This is called carbon 12 because when you add number of protons plus the number of neutrons, you get 12. Ta-da! Okay. Now let's do some space. I've got so many like little gadgets on my desk for this lecture. Well, for all my lectures, you just can't see them. Now let's do carbon 13. Protons, neutrons, electrons. This is carbon. Okay, it's carbon. How many protons does it have? 6. Because it's carbon, and carbon's atomic number is 6. And all atoms of carbon in the entire universe have 6 protons. Is that sinking in? I'm going to skip neutrons for a second. I'm going to go to electrons. There's 6 of them. But now let's look at the neutrons. Notice that this is carbon 13, not carbon 12. This is an isotope of carbon. And it means that it has the same number of protons, different number of neutrons than a standard atom. Same atomic number, different mass number. How do we figure out how many neutrons there are in an isotope, carbon 13? Well, normally we do 6 protons plus whatever neutrons is equal to the mass number, right? Well, no, our mass number is actually 13. So how do we figure out how many neutrons there are? If we want to do some simple math, 13 minus 6 is equal to 7. Therefore, there are 7 neutrons because 6 plus 7 is 13 to get carbon 13. Do another one, you say? Absolutely. Carbon has another isotope, carbon 14. These isotopes, by the way, are used in a variety of medical applications, from cancer location and treatment to things like radiometric dating to help identify how old an organic sample is that's found at like an archaeological site. Okay, so why did I do that? I didn't want to do that. I got ahead of myself. I got excited to do carbon 14 isotope stuff. All right, it's carbon. What's the atomic number? 6. How many protons? 6. Electrons? 6. Neutrons. Okay, so if this plus this is equal to our mass number, and our mass number is 14, how many neutrons do we have? 8. Okay, because 14 take away 6. Okay, you kind of understand how this works? So I won't go into all the details about isotopes. They're pretty cool. But a lot of times you'll think about radioactive isotopes that give off a ton of radioactive energy, things like plutonium and uranium and stuff like that. The reason that they do is that isotopes are unstable. Even smaller ones like carbon 6 and carbon 13 and carbon 14, they break down because they're not stable like carbon 12, and they don't like that. So they're trying to give off energy and break down so that they can get to a more stable configuration. Okay, so again, the big atoms like carbon, hang on, my brain's having issues. The big atoms like plutonium and uranium and some of these other ones, they give off lots of energy as they break down. Okay. All right. I am going to stop this lecture right here, not because we're done, but because this has been long enough, and I'm going to do the second half of this chapter in another lecture. So hang on, I'll see you in a second.